Hey, you all. Did you know that right now, as you're listening to this, the entire universe might be sitting on the edge of a catastrophic transformation? One so sudden and so total that it could erase everything we know, faster than the speed of light with no warning whatsoever. Sounds like science fiction, doesn't it? But this isn't made up for a movie or a novel. This is a real, serious possibility that physicists have been studying for decades. It's called vacuum decay. And it's tied to one of the most profound ideas in modern physics, the false vacuum theory. Now, before you panic, don't. The chances are astronomically small, but the implications are so enormous, so mind-bending that it's worth understanding. Because if vacuum decay were to happen, it wouldn't just destroy Earth or our solar system or even our galaxy. It would rewrite the very laws of physics across the entire observable universe, instantly, irreversibly, and without mercy. And the scariest part, it could, in principle, happen tomorrow. So how is that even possible? How can empty space, the vacuum, be unstable? What does it mean for the vacuum to decay? And why should we care about something that sounds more like metaphysics than measurable science? In this video, we're going to walk through the physics step by step. We'll start with what we mean by vacuum in physics, not just empty space, but the lowest possible energy state of the universe. Then we'll explore how quantum fields fill every point in space, even where there's nothing. We'll talk about the Higgs field, the discovery at the Large Hadron Collider, and why that discovery raised a terrifying question. Is our vacuum truly stable, or just temporarily stuck in a false state, like a ball perched on a hill, waiting for the slightest nudge to roll down into a deeper valley? We'll explain the concept of metastability, potential energy landscapes, quantum tunneling, and how a tiny bubble of true vacuum could form somewhere in the cosmos and expand at nearly the speed of light, converting everything it touches into a new reality governed by different physical laws. And yes, we'll even write out the key formulas in plain English, exactly as you requested, so you can follow the logic without getting lost in symbols. This isn't just speculation. It's grounded in Einstein's relativity, quantum field theory, and experimental data from particle colliders. And while the outcome is almost certainly not going to happen in our lifetime, or even in the next trillion years, it forces us to confront deep questions about the nature of reality, the fate of the cosmos, and whether the laws of physics themselves are permanent, or just temporary arrangements in an ever-changing quantum sea. So let's begin, not with doom, but with curiosity. Because understanding vacuum decay isn't about fear. It's about appreciating how delicate, how dynamic, and how astonishingly structured our universe really is. First, let's clear up a common misconception. When most people hear the word vacuum, they think of outer space, empty, dark, silent. Maybe a region with no air, no matter, nothing at all. But in physics, the vacuum is not nothing. In fact, according to quantum field theory, the framework that combines quantum mechanics and special relativity, the vacuum is teeming with activity. It's the stage upon which all particles and forces play out their roles, and that stage itself has properties. Every fundamental particle you've ever heard of, electrons, quarks, photons, is actually an excitation of an underlying quantum field. There's an electron field that fills all of spacetime. When that field vibrates in a certain way, we see an electron. Same for the photon field, the quark fields, and so on. Even in the complete absence of particles, these fields still exist, and they have a value, even in their calmest, quietest state. That calmest state is what we call the vacuum state. But here, the key. The vacuum state isn't necessarily zero. For some fields, like the electromagnetic field, the lowest energy state is indeed zero. You get no photons when it's quiet. But for other fields, like the Higgs field, the lowest energy state is not zero. In fact, the Higgs field has a non-zero value everywhere in space, even in the deepest vacuum. That's why particles have mass. Without that constant background hum of the Higgs field, electrons would zip around at light speed, atoms couldn't form, and chemistry and life would be impossible. So the vacuum isn't empty. It's a complex, structured medium defined by the values of all the quantum fields in their ground state, and the energy of that configuration, the total energy density of empty space, is what we call the vacuum energy. Now here, where things get interesting. In classical physics, a system always settles into its absolute lowest energy state. Think of a ball rolling down a hill until it reaches the bottom of the valley. Once it's there, it stays. But in quantum physics, things are more subtle. Because of quantum uncertainty and tunneling, a system can get stuck in a local minimum, a dip in the energy landscape that isn't the deepest possible valley. It's stable for now, but not forever. This is called a metastable state. Imagine a ball sitting in a small depression on the side of a mountain. From its perspective, it's at rest. If you give it a tiny push, it rolls back to the center of the depression. It seems stable, but if you give it a big enough push, or if, through pure quantum randomness, it suddenly appears on the other side of the ridge, it could roll all the way down to the true bottom of the mountain, releasing a huge amount of energy in the process. That's the essence of false vacuum theory. Our universe might be like that ball in the shallow depression. The vacuum we live in, the one that gives particles their masses, sets the strength of forces, and allows stars and planets to exist, might not be the true, absolute lowest energy state of the quantum fields. It might just be a false vacuum, stable for now, but capable of decaying into a lower energy state if triggered. And if that decay happens, even in one tiny region of space, the consequences would be cosmic. But how do we know whether our vacuum is true or false? That's where particle physics comes in, specifically the Higgs boson. The Higgs field is central to the standard model of particle physics. It's responsible for breaking electroweak symmetry and giving mass to the W and Z bosons, as well as to quarks and leptons. The shape of the Higgs potential, the mathematical function that describes its energy at different field values, determines whether the vacuum is stable, unstable, or metastable. In the simplest version of the theory, the Higgs potential looks like a wine bottle bottom or a Mexican hat, a high-energy peak at zero field value, and a circular valley of lower energy around it. The field rolls down and settles somewhere in that valley, picking a direction randomly. That's spontaneous symmetry breaking. But that's the classical picture. When we include quantum corrections, tiny effects from virtual particles popping in and out of existence, the shape of the potential can change dramatically at very high field values, far beyond what we can probe in labs. Calculations using the measured mass of the Higgs boson, about 125 GeV, and the mass of the top quark, about 173 GeV, suggest something startling. At extremely high energies, around 10 to the 16 GeV, close to the grand unification scale, the Higgs potential might dip below its current value. That would mean our vacuum is not at the global minimum. It's in a local minimum, a false vacuum. Let me say that again. Based on the best measurements we have, the equations of the standard model, when extrapolated to energies far beyond what we can test directly, indicate that the vacuum of our universe may be metastable. Now, that doesn't mean it's going to decay anytime soon. In fact, the predicted lifetime of a metastable vacuum is vastly longer than the current age of the universe. We're talking about expected decay times of 10 to the 100 years or more. So statistically, it's incredibly unlikely to happen in the next second or the next billion years. But unlikely is not the same as impossible. And because the decay, once started, would propagate at nearly the speed of light, there would be no warning. One moment, the laws of physics are as we know them. The next moment, poof, everything changes. So how would vacuum decay actually happen? It starts with quantum tunneling. Even though the energy barrier between our false vacuum and the true vacuum is enormous, quantum mechanics allows for a tiny probability that a bubble of true vacuum could spontaneously form somewhere in space. This isn't due to thermal fluctuations. Space is too cold for that, but purely due to the probabilistic nature of quantum fields. Think of it like radioactive decay. A single uranium atom has a very low chance of decaying in any given second, but over time, it will. Similarly, every cubic meter of space has an infinitesimal chance per unit time of nucleating a true vacuum bubble. If such a bubble forms, what happens next? The walls of the bubble contain an enormous amount of energy, the difference between the false and true vacuum states. This creates a pressure imbalance. Inside the bubble, the vacuum energy is lower. Outside, it's higher. As a result, the bubble expands outward, accelerating rapidly. According to general relativity, the expansion speed approaches the speed of light. Nothing inside the bubble can stop it. Nothing outside can detect it coming, because the bubble wall moves faster than any signal could warn us. As the bubble expands, it rewrites the laws of physics in its wake. The Higgs field inside settles into its new, lower energy value. That changes the masses of all particles. Electrons might become heavier or lighter. Quarks might not bind into protons anymore. The electromagnetic and nuclear forces might behave completely differently. Atoms, molecules, stars, life, none of it may be possible in the new vacuum. In short, everything we know would cease to exist, not with a bang, but with a silent, unstoppable wave of new physics. Now let's talk about the math, but in words as you asked. The key quantity is the vacuum energy density. In Einstein's theory of general relativity, energy density curves spacetime. The relationship is captured in the Einstein field equation, which we can express in words as: the curvature of spacetime equals 8 pi times the gravitational constant times the energy and momentum content of space, plus the cosmological constant term. But for vacuum decay, the critical formula comes from quantum field theory, the decay rate per unit volume per unit time. This is given by an expression derived by Sidney Coleman in the 1970s. In plain English, it's the probability per cubic meter per second that a true vacuum bubble will form equals a prefactor that depends on the details of the field, multiplied by the exponential of negative, the bounce action divided by Planck's constant. The bounce action is a number that measures how hard it is for the field to tunnel through the energy barrier. The larger the bounce action, the smaller the decay rate. And in our universe, calculations show the bounce action is huge, so the exponential suppression makes the decay rate unimaginably small. For example, if the bounce action is about 400, then the decay rate is proportional to e to the power of negative 400. That's a number so small it's effectively zero for all practical purposes. To put it in perspective, e to the negative 400 is about 10 to the negative 174. That means you'd need to watch a volume of space, the size of the observable universe for many times the current age of the universe before you'd expect to see even one bubble form. So again, no need to lose sleep over this. But let's dig deeper into why the Higgs potential might turn downward at high energies. The shape of the Higgs potential isn't fixed. It runs with energy scale due to quantum loop corrections. The main players are the top quark and the Higgs boson itself. The top quark is extremely heavy, about 173 times the mass of a proton, and it couples very strongly to the Higgs field. Because of this strong coupling, virtual top quarks in quantum loops tend to pull the Higgs potential downward at high field values. On the other hand, the Higgs self-interaction tends to push it upward. The balance between these effects determines the fate of the vacuum. If the top quark were a bit lighter, or the Higgs a bit heavier, the potential would stay positive forever, and our vacuum would be absolutely stable. If the top were heavier or the Higgs lighter, the potential might already be negative, meaning our vacuum would be unstable and should have decayed long ago, which obviously didn't happen, so that scenario is ruled out. But right in the middle, where our measurements place us, is the metastable zone. The potential dips below zero only at energies far beyond what we can probe, and the barrier is high enough that tunneling is exceedingly rare. This is why the precise measurement of the Higgs and top masses was so crucial. Before the Large Hadron Collider confirmed the Higgs mass in 2012, we didn't know which side of the stability line we were on. Now, with better data, the consensus among particle physicists is that we're likely in the metastable region, but with large uncertainties, especially in the top quark mass. Even a shift of 0.5% in the top mass could tip the balance toward absolute stability. Moreover, this whole calculation assumes that the standard model is valid all the way up to the Planck scale, about 10 to the 19 GeV. But that's almost certainly not true. We know the standard model is incomplete. It doesn't include gravity, dark matter, neutrino masses, or cosmic inflation. New physics, like supersymmetry, extra dimensions, or grand unified theories, could easily modify the running of the Higgs potential and stabilize the vacuum completely. So while the false vacuum scenario is theoretically possible within the standard model, it's highly dependent on assumptions that may not hold in reality. Still, it's a powerful reminder. The laws of physics we take for granted might not be eternal. They could be contingent, temporary features of a cosmic phase that could end at any moment. Now, let's consider what would happen inside the bubble of true vacuum. Once the Higgs field rolls down to its new minimum, the vacuum expectation value changes. Let's say it becomes much larger or much smaller than its current value of 246 GeV. That would alter the Yukawa couplings, the interactions that give fermions their mass. So the mass of every quark and lepton would change proportionally. If the new Higgs value were 0, all particles would become massless. Electromagnetism and the weak force would reunify into the electroweak force. Atoms couldn't form because electrons wouldn't be bound to nuclei. Chemistry would vanish. If the new value were much larger, particles might become so heavy that even protons and neutrons couldn't exist. Or the strong force might behave differently, preventing nuclear binding. In either case, the structure of matter as we know it would disintegrate. Stars would stop fusing. Black holes might evaporate differently. Spacetime itself might have a different cosmological constant, possibly negative, which would cause the interior of the bubble to collapse in on itself in a big crunch. Some models even suggest that the new vacuum could have fewer spatial dimensions or different fundamental constants. The speed of light, Planck's constant, the gravitational constant, all could be different. There's no guarantee that life, or even complex structures, could exist in the new phase. It might be a sterile, featureless void. And because the bubble expands at nearly light speed, there's no escape. Even if you saw it coming, which you wouldn't, you couldn't outrun it. No signal, no spaceship, no information can travel faster than light. So the first sign of vacuum decay would be the last. But here's a strange thought. Maybe vacuum decay has already happened, somewhere far away in the universe. If a bubble formed billions of light years from us, it might still be traveling toward us unseen. We wouldn't know until it arrived. However, observations of the cosmic microwave background and the large-scale structure of the universe show no evidence of such bubbles colliding with our region. If vacuum decay were common, we'd expect to see imprints in the sky, distortions from bubble collisions in the early universe. We don't see those, so either decay is exceedingly rare, or it hasn't happened anywhere in our past light cone. Another angle, could we trigger vacuum decay ourselves? Some people worried that high-energy particle colliders like the LHC might create conditions that spark a phase transition, but that's been thoroughly studied and dismissed. The energies reached in the LHC are trillions of times lower than the scale where the potential turns negative. Cosmic rays, natural particles from space, have been bombarding Earth and other celestial bodies with far higher energies for billions of years. If such collisions could trigger decay, it would have happened already. So human experiments pose no risk. Now let's clarify a subtle point. Vacuum decay is not the same as the Big Crunch or heat death. Those are scenarios based on the expansion of the universe and thermodynamics. Vacuum decay is a quantum event that changes the fundamental laws, not just the arrangement of matter. Also, it's not related to black holes or singularities. It's a property of the quantum vacuum itself. One more thing. The term vacuum energy is also used in cosmology to describe dark energy, the mysterious force accelerating the expansion of the universe. But that's a different concept. The cosmological constant in Einstein's equations represents a constant energy density of space, which acts like a repulsive gravity. Whether this is the same as the Higgs vacuum energy is unknown. They differ by about 120 orders of magnitude, which is the biggest unsolved problem in theoretical physics, known as the cosmological constant problem. So don't confuse dark energy with the Higgs vacuum instability. They're separate issues, though both involve the energy of empty space. Back to the decay process. The bubble doesn't just expand, it accelerates. Why? Because the pressure difference between the inside and outside creates a kind of tension that drives the wall outward. In the thin wall approximation, a simplification used in calculations, the bubble wall quickly reaches ultra-relativistic speeds. Inside the bubble, the field oscillates around its new minimum, releasing energy as particles. But those particles are governed by the new physics, so they're unrecognizable to us. From the outside, the bubble looks like a sphere of intense energy, but since it moves at light speed, it's causally disconnected from the rest of the universe until it arrives. Now imagine you're an observer far from the nucleation site. You're living your life unaware. Then in an instant, a wall of new physics sweeps over you. Your body, your planet, your star, all are instantly reconfigured according to new laws. Consciousness, memory, identity, gone. Not destroyed in a fiery explosion, but erased by a change in the rules of reality. It's the ultimate existential reset button. But again, this is not something to worry about. The probability is so low that you're far more likely to be struck by lightning while winning the lottery and being hit by a meteor, all on the same day. Still, the idea forces us to rethink what fundamental really means. Are the laws of physics written in stone, or are they more like local customs, valid here and now, but subject to change if the cosmic phase shifts? This connects to deeper philosophical questions. In the multiverse hypothesis, for example, different regions of spacetime might settle into different vacuum states, each with its own laws. Our universe would be just one bubble among countless others, each with different constants, particles, and possibilities. In that view, vacuum decay isn't destruction, it's just a transition to another branch of the multiverse. But we have no evidence for the multiverse yet. It remains speculative. What we do have is solid math, experimental data, and a consistent theoretical framework that allows for the possibility, however remote, of vacuum decay. Let's recap the key points so far. 1. The vacuum in physics is not empty. It's the ground state of quantum fields. 2. The Higgs field gives particles mass and has a non-zero value in our vacuum. 3. Due to quantum effects, the Higgs potential might have a lower energy state at very high field values. 4. If so, our vacuum is metastable, a false vacuum. 5. Quantum tunneling could, in principle, create a bubble of true vacuum. 6. That bubble would expand at nearly light speed, rewriting the laws of physics. 7. The predicted lifetime is vastly longer than the age of the universe, so it's not a practical concern. 8. New physics beyond the standard model could easily stabilize the vacuum. 9. Human experiments cannot trigger it. 10. Observations show no signs it has happened nearby. Now let's go deeper into the mathematics, again in words. The Higgs potential in the standard model, including quantum corrections, can be approximated as the energy density of the Higgs field equals 1/2 times the square of the Higgs field value times the square of the Higgs mass parameter, plus 1/4 times the Higgs self-coupling constant times the 4th power of the Higgs field value. At low energies, the self-coupling is positive, so the potential has a minimum away from zero. That's our vacuum. But the self-coupling changes with energy scale. Its rate of change is governed by the renormalization group equations, which account for how virtual particles affect the interaction strength. The dominant contribution to the running of the Higgs self-coupling comes from the top quark loop, which is negative and proportional to the 4th power of the top Yukawa coupling. So as energy increases, the self-coupling decreases. If it becomes negative at some high scale, the potential curves downward, and the energy density can become lower than in our current vacuum. The critical scale where this happens is called the instability scale. Current estimates place it around 10 to the 10 to 10 to the 16 GeV. The bounce solution, the field configuration that describes the tunneling event, is found by solving the Euclidean equation of motion. In plain terms, this means finding the path the field takes through an imaginary time dimension that minimizes the action. The resulting bounce action is approximately 27 pi squared times the cube of the barrier height, divided by the square of the barrier width, times the difference in vacuum energy. But since the barrier is very wide and high, the action is large, making the decay rate exponentially suppressed. Another way to think about it, the lifetime of the false vacuum is proportional to the exponential of the bounce action divided by Planck's constant. Since Planck's constant is tiny, even a modest action leads to an enormous lifetime. For our universe, the estimated lifetime is greater than 10 to the 100 years. The universe is only 1.4 times 10 to the 10 years old, so we're safe. Moreover, the expansion of the universe works against bubble formation. In an accelerating universe driven by dark energy, distant regions move apart faster than light, so they can't influence each other. This actually reduces the chance that a bubble will form within our causal horizon. In fact, some calculations suggest that in a de Sitter universe like ours, the decay rate is further suppressed by the Gibbons-Hawking temperature, a tiny thermal effect due to the cosmological horizon. So multiple factors make vacuum decay even less likely than naive estimates suggest. Still, the theoretical possibility remains, and it's a stunning example of how quantum field theory and cosmology intersect to address questions about the ultimate fate of reality. In the next part of this video, we'll explore historical context, how this idea developed from early quantum mechanics to Coleman's breakthrough papers, and we'll examine alternative scenarios like thermal vacuum decay in the early universe, and whether inflation could have already triggered a phase transition. We'll also discuss philosophical implications. If the laws of physics aren't eternal, what does that say about the nature of truth, knowledge, and existence? Now that we've laid the groundwork, understanding what the vacuum really is, why it might be unstable, and how vacuum decay could unfold, let's step back and look at how this idea emerged historically. Because like so many profound concepts in physics, false vacuum theory didn't spring fully formed from a single mind. It evolved through decades of theoretical breakthroughs, driven by questions about symmetry, phase transitions, and the quantum nature of reality. The story begins not with cosmology, but with condensed matter physics. In the 1930s and 1940s, physicists studying materials like superconductors and magnets noticed something remarkable. Systems could undergo sudden changes in their properties when cooled or heated past a critical point. Ice melts into water. Iron loses its magnetism above the Curie temperature. These are called phase transitions. But not all phase transitions are the same. Some, like boiling water, involve latent heat and coexist phases, bubbles of steam in liquid water. These are first-order phase transitions. Others, like the loss of magnetization in iron, happen smoothly with no discontinuity. Those are second order. In the 1960s, physicist Yoichiro Nambu drew a bold analogy. Maybe the universe itself underwent a phase transition in its early moments. He proposed that symmetries present at high energies could be hidden or broken at lower energies, just like the rotational symmetry of liquid water is broken when it freezes into crystalline ice, which has a preferred orientation. This idea of spontaneous symmetry breaking became central to particle physics. In 1964, Peter Higgs, Francois Englert, Robert Brout, and others showed how a field-filling space could break electroweak symmetry and give mass to particles without violating the underlying laws. That field, now called the Higgs field, became the cornerstone of the Standard Model. But here, the key insight. Phase transitions in fields can also be first order. And in a first-order transition, the system doesn't change smoothly. Instead, it gets stuck in a metastable state, like supercooled water that remains liquid below 0 degrees Celsius until a disturbance triggers sudden freezing. In the cosmic context, that means the early universe might have been trapped in a high-energy vacuum state after inflation. As it cooled, it should have rolled down to the true vacuum. But if the transition was first order, it might have proceeded via bubble nucleation, tiny regions of true vacuum forming and expanding, colliding and eventually filling space. This is exactly what Sidney Coleman and his collaborator Frank DeLucia explored in the late 1970s. Building on earlier work by John Wheeler and others on quantum tunneling, Coleman developed a mathematical framework to describe how a scalar field, like the Higgs, could tunnel through an energy barrier in spacetime. His famous 1977 paper, Fate of the False Vacuum, revolutionized our understanding. He showed that in quantum field theory, the decay of a metastable vacuum isn't gradual. It happens through the spontaneous formation of bubbles, each acting as a seed for a new phase of reality. And crucially, he included gravity in the calculation. In their 1980 follow-up, Gravitational Effects on and a Vacuum Decay, Coleman and DeLucia demonstrated that gravity could either suppress or enhance the decay rate, depending on the energy difference between vacua. If the true vacuum has negative energy density, for example, the bubble interior might collapse into a black hole, halting expansion. If it's positive but smaller than the false vacuum, the bubble still expands, but gravity slightly slows it. If the true vacuum has higher energy, which would be bizarre since we assume it's lower, then the whole picture changes. But in our case, the concern is a lower energy true vacuum, so the bubble expands relentlessly. Now, let's clarify a subtle but important distinction. There are two ways vacuum decay can occur: quantum tunneling and thermal fluctuations. Quantum tunneling, as we've discussed, can happen even at absolute zero. It's purely probabilistic, driven by the uncertainty principle. This is the dominant mechanism in today's cold, empty universe. But in the hot, dense early universe, just fractions of a second after the Big Bang, thermal effects were dominant. Particles had enormous energies, and the Higgs field was jostled constantly by collisions. In that environment, the field could have been kicked over the energy barrier classically, without needing quantum tunneling. This is called thermal vacuum decay, and it's actually more efficient than quantum tunneling at high temperatures. So why didn't the universe decay then? Because in the early universe, the effective Higgs potential was different. At high temperatures, thermal corrections add a positive term proportional to the square of the field value. This lifts the potential near zero, restoring electroweak symmetry. The Higgs expectation value was zero in the very early universe. As the cosmos expanded and cooled, the thermal correction shrank. Around 10 to the minus 12 seconds after the Big Bang, the universe underwent the electroweak phase transition. The Higgs field condensed into its current non-zero value. Now, whether that transition was smooth second order or abrupt first order depends on the Higgs mass. With a light Higgs, it's a smooth crossover. With a heavy Higgs, it could be first order. But we now know the Higgs is relatively light, 125 GeV, so the transition was almost certainly a smooth crossover. That means no bubbles formed, no violent phase change, and no risk of getting stuck in a false vacuum back then. However, if there are other scalar fields beyond the standard model, like those in supersymmetry or grand unification, they might have undergone first-order phase transitions. And if one of those fields is coupled to the Higgs, it could indirectly affect vacuum stability. This is why cosmologists study gravitational waves from the early universe. A strong first-order phase transition would generate ripples in spacetime, detectable by future observatories like LISA. So far, no such signal has been found, but it remains a promising window into high-energy physics. Returning to the present day, even though thermal decay is irrelevant now, quantum decay remains a theoretical possibility. And while the probability is tiny, it's not zero. But let's address a common misconception. Vacuum decay is not the same as vacuum energy causing accelerated expansion. Dark energy, the force behind cosmic acceleration, is often modeled as a cosmological constant, which is a form of vacuum energy. But that energy is positive and constant. In contrast, the Higgs vacuum instability involves a potential that becomes more negative at high field values. These are separate contributions to the total vacuum energy. In fact, the measured dark energy density is about 10 to the minus 9 joules per cubic meter, while the naive Higgs vacuum energy is around 10 to the 113 joules per cubic meter, off by 122 orders of magnitude. This cosmological constant problem remains unsolved, and it suggests our understanding of vacuum energy is deeply incomplete. So when we talk about vacuum decay, we're focusing only on the Higgs sector's potential shape, not on dark energy. Now, let's consider a fascinating twist. What if our vacuum is not just metastable, but part of a vast landscape of possible vacua? This idea comes from string theory. In string theory, the extra dimensions of space are compactified, curled up into tiny shapes called Calabi-Yau manifolds. The way they're curled determines the effective laws of physics in our four-dimensional world: particle masses, force strengths, even the number of generations of matter. There may be as many as 10 to the 500 different ways to compactify these dimensions, each corresponding to a different vacuum state with different physical constants. This is the string theory landscape. In this view, our universe is just one valley in a colossal mountain range of possibilities. An eternal inflation, a theory where some regions of spacetime keep inflating forever, could populate this landscape with countless bubble universes, each in its own vacuum. In such a multiverse, vacuum decay isn't destruction. It's just a local transition to another habitable or uninhabitable region. And from a global perspective, the multiverse might be eternally renewing itself through these decays. But again, this is highly speculative. String theory lacks experimental confirmation, and the landscape idea is controversial. Many physicists argue it's not falsifiable and therefore not scientific. Still, it shows how vacuum decay connects to some of the deepest questions in theoretical physics. Why do the constants of nature have the values they do? Is our universe fine-tuned for life? Could other forms of physics support complexity? If vacuum decay is possible, then the laws of physics are not immutable truths. They're contingent outcomes of cosmic history. Now let's return to the math, but carefully in words as you requested. The decay rate per unit volume, gamma, is given by gamma equals a times the exponential of negative b divided by h bar, where a is a profactor with units of inverse time times inverse volume. B is the Euclidean action of the bound solution, and h bar is the reduced Planck constant. The bounce action B is calculated by integrating the difference between the field's kinetic and potential energy over four-dimensional Euclidean space. That is, space with imaginary time. For a single scalar field with a potential that has a local minimum at phi equals v and a deeper minimum at phi equals w, the bounce solution is spherically symmetric in 4 dimensions. The field starts near v at the center, rolls over the barrier, and approaches v again at infinity. The resulting action is approximately B equals 27 pi squared times sigma cubed, divided by 2 times the absolute value of the difference in vacuum energy density squared, where sigma is the surface tension of the bubble wall, the energy per unit area. Surface tension itself depends on the shape of the potential. Roughly, sigma equals the integral from v to w of the square root of 2 times the potential energy difference d, phi. In practice, for the Higgs field, these quantities are computed numerically using renormalization group improved potentials. Current estimates give B over h bar on the order of 400 to 500. Since e to the negative 400 is about 10 to the negative 174, the decay rate is unimaginably small. To put this in perspective, the observable universe has a volume of about 4 times 10 to the 80 cubic meters. Multiply that by the age of the universe in seconds, about 4.3 times 10 to the 17, and you get the total number of opportunities for decay to occur. Even then, the expected number of bubbles is gamma times volume times time, which is still vastly less than 1. So statistically, it almost certainly hasn't happened yet in our cosmic neighborhood. Moreover, because the universe is accelerating due to dark energy, distant regions are receding faster than light. This means our future event horizon limits the volume of space that can ever influence us. Within that causal patch, the probability of decay is even smaller. Some theorists have even argued that in an eternally inflating universe, the concept of decay rate becomes ambiguous because time itself is ill-defined across different patches. But for practical purposes, within our observable universe and foreseeable future, vacuum decay is not a threat. Now, let's consider an alternative scenario. What if the true vacuum isn't completely lethal? Most discussions assume that any change to the Higgs vacuum expectation value would destroy atomic structure. But is that necessarily true? Suppose the new minimum is only slightly different, say, the Higgs value changes by 10%. Then particle masses would shift, but atoms might still form. Chemistry could be altered but not impossible. Life, in some exotic form, might still be viable. However, calculations suggest that even small changes can have catastrophic effects. For example, if the up and down quark masses shift relative to each other, protons might become heavier than neutrons, making hydrogen unstable. Or if the electron mass increases too much, atoms shrink and chemical bonds weaken. The universe appears to be finely balanced. Change one parameter and stars don't form. Change another and carbon isn't produced in stellar cores. This is the basis of the anthropic principle. We observe the constants we do because only in such a universe can observers exist. If vacuum decay leads to a sterile vacuum, then we wouldn't be around to see it, which is consistent with our continued existence. But if some true vacua are life-permitting, then perhaps vacuum decay could lead to new forms of complexity. We simply don't know. Another angle: could intelligent beings survive or even trigger a controlled vacuum transition? Science fiction has explored this, civilizations engineering a new vacuum to escape cosmic doom. But in reality, the energy scales involved are far beyond any conceivable technology. You need to manipulate fields at 10 to the 16 GeV, while our most powerful collider reaches about 10 to the 4 GeV. That's a trillion times too weak. And even if you could, you couldn't control the outcome. The new vacuum's properties are determined by fundamental physics, not by choice. So no, we can't engineer a safer vacuum. We're stuck with the one we have, hopefully for a very long time. Now let's address a philosophical question. If the laws of physics can change, what does that say about the nature of scientific truth? For centuries, scientists assumed that the laws were eternal and universal. Newton's gravity worked the same on Earth and in the heavens. Maxwell's equations described light everywhere. Einstein extended this to all frames of reference. But vacuum decay suggests that the laws we measure are just the low-energy effective description of a particular vacuum state. In another vacuum, the effective laws would be different, even if the underlying theory, like string theory or quantum gravity, is the same. This doesn't make science arbitrary. Within our vacuum, the laws are stable and predictable. Experiments are reproducible. Technology works. But it does mean that the laws aren't necessarily fundamental, they're emergent. This is a profound shift in perspective. It moves us from a static view of reality to a dynamic, evolutionary one, where the universe can undergo radical transformations, and what we call physics is just a local dialect of a deeper cosmic language. Some physicists find this unsettling. Others find it liberating. It opens the door to a richer, more varied cosmos, one where diversity isn't just in galaxies and stars, but in the very rules that govern them. But again, this remains speculative. Until we detect evidence of other vacua or observe a decay event, we must treat our vacuum as the only one. Now, let's consider observational constraints. Astronomers have searched for signs of vacuum decay in several ways. First, they look for imprints of bubble collisions in the cosmic microwave background, the afterglow of the Big Bang. If our universe collided with another bubble during inflation, it would leave a disk-like pattern of temperature variations. Extensive searches by Planck's satellite data have found no such signatures. Second, they study the distribution of galaxies and cosmic voids. A passing bubble wall would distort large-scale structure, but no anomalies have been detected. Third, they consider the longevity of ancient astrophysical objects. White dwarfs, neutron stars, and old stars have existed for billions of years. If vacuum decay were likely, some of them should have triggered it via high-density effects. They haven't. All these observations support the conclusion that vacuum decay, if possible, is exceedingly rare. Moreover, the success of the Standard Model up to the TeV scale gives us confidence that no unexpected instabilities lurk at accessible energies. So while the extrapolation to ultra-high energies carries uncertainty, there's no evidence to suggest imminent danger. Let's also clarify what wouldn't happen if decay occurred. It wouldn't be an explosion. There would be no fireball, no shockwave in the conventional sense. The bubble wall is a thin region where the field changes rapidly, but it doesn't carry matter. It carries information about the new vacuum state. Inside the bubble, space might contract if the new vacuum has negative energy, leading to a big crunch, or it might expand differently. But from the outside, the transition is invisible until it arrives. And because it moves at light speed, causality ensures that no observer can see it coming. Your last thought would be ordinary, then nothing. But again, this is not a realistic concern. Now, let's imagine a different kind of instability, not in the Higgs field, but in the QCD vacuum, the strong force sector. Quantum chromodynamics, the theory of the strong force, also has a complex vacuum structure with instantons and theta angles. But this vacuum is believed to be absolutely stable. No decay channel is known. Similarly, the electromagnetic and weak sectors don't exhibit this kind of metastability. So the Higgs is special in this regard, because it's a scalar field with a self-interaction that can turn negative. Other hypothetical scalar fields, like the inflaton or moduli fields in string theory, could also be metastable, but we have no evidence they exist. Thus, the Higgs remains the only known candidate for vacuum decay in established physics. Finally, let's reflect on why this idea captivates us. It's not just the drama of cosmic doom. It's the realization that reality is more fluid than it appears. The ground beneath our feet, the very fabric of spacetime, is not solid, but poised, delicate, sustained by balances so precise they verge on the miraculous. And yet it has held for nearly 14 billion years. Stars have formed, planets have coalesced, life has arisen, all within this fragile equilibrium. That's not a reason for fear, it's a reason for awe. So could the universe collapse tomorrow? Technically, yes, it's not forbidden by the laws of physics. But realistically, no. The odds are so vanishingly small that you'd have better luck winning every lottery on Earth for 1,000 years straight. The real value of this idea isn't in predicting disaster, but in deepening our understanding of the universe's structure, stability, and potential. It reminds us that physics isn't just about what is, it's about what could be. And in exploring those possibilities, we come closer to grasping the true nature of existence. So sleep well tonight. The vacuum is holding, and while you rest, the cosmos continues its quiet, majestic dance, governed by laws that, for now, remain beautifully, reliably ours.